All right, so let's continue. Yesterday we have started discussing about carrier transport phenomena, and let's recap on the two modes of carrier transport. So what are the two modes of carrier transport of the carriers? How do they move in the semiconductor? What's the first one? How do the carriers move in semiconductor? Okay, drift and diffusion, right? Good, drift and diffusion. Okay, so in order for drift to happen, what do we have to have? What is the requirement? Okay, good, electric field. You need to have electric field in order for you to have drift. Okay, so how about the other one? Diffusion. What is required for diffusion to take place? Concentration gradient, yes, good. Right, what is concentration gradient? What do you understand by concentration gradient? What does it mean by concentration gradient? What do you think it means? Any ideas? Okay, concentration gradient is related to movement of carriers, in this case, from high concentration region to low concentration region. Okay, from high concentration region to low concentration region. So that means if you have two regions of different concentration, so we're gonna have different concentration gradient. Contoh, apa contoh yang paling simple? Okay, high concentration to low concentration. Pada bancuh teh tak? Hari puasa tanya pasal teh pula. Pernah bancuh air teh? Nah, Milo ke? Biasa bancuh. Do you get to see any concentration gradient while making your tea or something? Pernah tengok tak concentration gradient dalam air teh? How does it look like? Amirul, how does it look like? What is the proof that you have concentration gradient in your tea? How do you tell? Amirul? Tersebar warna teh, right? So the color is distributed. Yang lazat, yang lazat. Sekarang pukul 10 pagi ya. So, yeah, so you can see the color is distributed, right? So mula-mula kita letak air panas. Letak macam teh first, and then letak air panas. And then we stir, right? We stir the tea. As you stir, you can see that the tea is distributed and eventually becomes uniform across your cup. So itu concentration gradient. So maksudnya is moving from high concentration gradient dalam the tea bag, from the tea bag to low concentration gradient in the hot water and eventually distributed in the whole cup, right? So that's a very simple example of concentration gradient. So carrier semua macam tu juga. So it's moving from high concentration gradient to low concentration gradient. So we're going to see later on when we have a p-n junction, and when you join a junction, one side consists of n-type and the other side consists of p-type. So the moment you joined, we're going to see that your carriers will be distributed across the original region. Okay, so electrons from the n-type are going into p-type, and on the other hand, holes from the p-type are going into n-type. Sebab dia nampak concentration gradient, right? So the original region has high concentration and the neighboring region has low concentration. So that's why it's migrating towards low concentration gradient, low concentration region in order to establish equilibrium. Okay, sama macam bacote. So we learn about drift and we learn about diffusion. So drift requires electric field, whereas diffusion requires concentration gradient. Okay. So we have also learned about the dependence on mobility on doping, and we have seen that when you increase the doping level in your semiconductor, either in n-type or p-type, we're going to see a reduced mobility of the carriers. Okay, for example, in this case, if you look at electron, for example, electron mobility, if you dope from 1014 to 1016, you don't see much change. However, there's a gradual change. The slope is very, very low from 10 to the 14 to 10 to the 16. It's very low, low gradient. Okay, but when you go beyond 1016, and you increase the doping level beyond 1016, you'll start seeing a more significant change in the reduction to both electrons and holes mobility. Okay, hold on, let me improve. Okay, so we've also seen the dependence on mobility to the doping and temperature. If you see the one with low doping level from 1014 to 1017, say up here, to the one up here, sorry, all these up there. So you can see that when the temperature is increased from left to right, so the mobility reduces. The mobility reduces in a straight line, okay, almost in a straight line. Okay, so from 1014 to 1016, and this shows the dependence on the temperature. Okay, mobility on the temperature, where this is contributed by enhanced lattice scattering at high temperature. Okay, enhanced lattice scattering at high temperature. But when you increase your doping level to beyond 1017, so that is 1018 and 19, which is heavily doped. So we'll see two different mechanisms dominating at different temperatures. So at low temperature, the mobility will be dependent on the impurity scattering, which is dependent on the doping. Okay, the doping. So in this case, and at this point, the mobility increases when the temperature increases. Okay, so mobility increases as temperature is increased, even though the increase is not that great. However, when we increase the temperature to beyond 300 or more, Kelvin, we can see that lattice scattering starts to dominate, and the mobility shows the same trend as the low doping concentration. Okay, so it goes down again, but this only happens at high temperature for heavily doped semiconductors only. Okay, so for heavily doped, it's not that straightforward. There are two different mechanisms dominating at different temperatures, whereas at low temperature is more dependent on the impurity scattering, and at high temperature it's going to be dependent on lattice scattering. Whereas for low doping, it's going to be more related to the lattice scattering. Okay, so for lightly doped 1014 also lattice scattering dominates. So mobility decreases as temperature increases. So we've discussed about the almost straight line. However, when it's heavily doped, the impurity scattering will be more pronounced at low temperature. So the one with the increasing trend, low temperature. Mobility increases as temperature increases. So this is the first part of the curve, the front part with the positive gradient. However, for the high temperature case, so lattice scattering dominates and the trend follows the trends for the low doping semiconductors. So this is another representation of the topic of the issue. So dependence on temperature and doping as well. So you can see here electron and hole mobilities in silicon for various doping concentration. Okay, so this one is for electron is on the left hand side. You can see mu n here for electrons, and this mu p for hole. Okay, so you can also label this as mu e and mu h. Okay, if you want to use mu e or mu h, just be consistent. Either you want to use n or p or e or h. Just be consistent throughout. Don't use n and p in some cases and e and h in some other cases. Just try to be consistent. Okay, so same trend that you can see here. So another one, electron and hole mobilities versus impurity concentration for germanium, silicon, and gallium arsenide. Okay, so germanium is the first one, silicon and gallium arsenide. Right? So, okay. So if you can see from this graph, this tree graph, for the three different semiconductor materials, say if we are working with 1016 doping level and n-type, say n-type 1016, which one has the highest electron mobility? Which semiconductor has the highest electron mobility? N-type 1016. Majority carriers electrons. Which one among the three? Silicon or germanium or gallium arsenide? Anyone? Look at 1016. Okay, gallium arsenide. Look at gallium arsenide 1016. What's the value there? For mu n. So since it's n-type, look for mu n. Mu n there is somewhere 7 or 8, right? 7 or 8, 10 to the 3, isn't it? Right? 7 or 8, high 10 to the 3. So for silicon, on the other hand, if you look at mu n at the same doping level, so that's like 1, yeah, low 10 to the 3, right? Low 10 to the 3. 1 point something to 2, 10 to the 3. Okay, how about germanium? Mu n. That's about 2, 3, maybe 3 times 10 to the 3. Yep. So silicon is the lowest, germanium is the second, and the second highest, and gallium arsenide is the highest one. Why do you think this mu n or mu p properties is important? Where do you want to use this mu parameter in the device? Why the mobility is important? Since gallium arsenide is the highest one in terms of the mobility, what is the best device to make out of gallium arsenide in this case? The highest electron mobility if you compare to these three. Sesuai guna untuk buat apa? Anyone? Mu. LED. Yes, but it's not really due to the LED. It's not really due to the mu. It's different thing. It's more towards the direct band gap. Mu, why is it important? Mu is what is mu? Carrier mobility, right? So how quick the carrier moves. So it's related to the speed. Mu speed. When you talk about speed, device apa yang cross your mind? What device crosses your mind? Speed. Computer, right? Computer is a product lah. So what runs the computer? Processor. What runs the processor? What makes the processor? Chip, right? Chip, IC. What makes the IC? What is in the IC? Transistor, right? Transistor. So kalau nak dapat high speed transistor, faster switching, yang laju, high speed, high frequency, you have to go for gallium arsenide if you compare these three. Okay, so that's the importance of these parameters. So that's why we need to know this. That's why we need to understand what is mu, how do we calculate mu, what affects mu, okay, for electrons and holes. So this is one of the applications of mu, the usage of mu. So in this case, is related to the speed. Mu is, if you look at the definition I gave you in the group yesterday, so what did it say? Let me reopen the thing. Carrier mobility is the measure of ease of charge carrier movement, drift. That is a measure of how quickly a charge carrier can move through a material, how quickly, how fast, how quickly an electron can travel through a semiconductor. So if you want your device to be fast, you need your carrier mobility to be high, right? Because mu is proportional to the speed of your device. So in this case, if we're talking about the chip, so which is made by transistors, billions of transistors. So you want your transistors to be super fast. So that's why you need to have a very high mu, and that's why we need to learn about mu and what affects the mu, right? And how does the value of mu differ from one semiconductor to another one? So that if you want to make the transistor for the right purpose, you need to choose the right semiconductor material to begin with. Right, so now let's look into drift. So up to this point, we've considered drift, transport of electrons. We've covered a little bit on diffusion as well, but not yet in depth. So all these discussions previously are applicable for both electrons and holes. So we've seen about the movement of electrons and holes when you have electric field in the semiconductor material, just like what we saw on the animation yesterday, right? So you're going to see a net movement of carriers into specific direction for electrons and for holes. And that's how we realize a carrier separation in the device later on. When you generate your electron hole pairs in the device, so when you want to separate electron hole pairs into different direction, you need to use electric field to drive carrier separation. You cannot leave it to fate for them to separate, because there will not be any net movement, and there'll be recombination and annihilation of the carriers. We're going to see later on in the next topic about generation and recombination. So we've learned about this expression yesterday as well. So the current density is given by conductivity times electric field, and conductivity can be classified into two. One is contributed by electrons and one is contributed by holes, right? So you need to see the question. If you want to do the calculations later on, we're going to see, you need to see which one dominates and whether the one that doesn't dominate will contribute to sufficient sufficient current density to the overall current density, right? So we're going to see later on in the calculation anyway. So J total will be equal to JE belongs to electron, and JH current density belongs to hole, which is made up of Q, mu, and E, electron charge times mobility of electron times electron density or dopant concentration for electrons, for example, times electric field plus another component from hole. The very same thing, Q times mu H times density of holes times electric field. So now see the movement, the direction of movement, okay? So look at Q here. Q here, if Q is moving against to the right, for example, hole will be moving to the left in the direction of electric field, and JE will be in the direction of hole, okay, sama direction dengan hole, whereas okay, JE will be in the same direction of hole or the opposite direction of electron, because it's okay, the electron has the opposite direction, okay, the movement in terms of movement, so current will be in the opposite direction, whereas for hole the current will be in the direction of the movement, okay. So tengok direction kat sini, so don't be confused later on when you do the total current summation. So drift current density can be simplified as this, as what we saw on previous page. So J drift be equal to Q and mu E. You can factorize. So this E here on the front is actually the Q, so you can use either one, Q or E is fine, as long as you are consistent. So you can factorize this and you leave mu N times N, or mu E times N if you like, plus another component from hole, mu H times P, or mu P times P times electric field. And that is also simplified as conductivity times electric field, okay? So conductivity is given by ohm cm inverted, okay, because we have discussed before that conductivity is the inverse of resistivity, and resistivity is given by ohm cm, right? And it's a function of electron and hole concentration and mobilities as well. Okay, mobilities are functions of impurity concentration, we've discussed before, conductivity, so it also dependent on the impurity concentration in the using the equation that we have discussed before. For a given temperature, mobility decreases. We've discussed just now. With recap, mobility decreases with increasing impurity concentration because of enhanced impurity scattering. But if you look at this at high doping levels, so you need to discuss about the shape of the curve, where at low temperature is going to be dominated by impurity scattering, and at high temperature is going to be more dominated by lattice scattering at heavy doping, right? At heavy doping, beyond 1017, 18, and 19. Okay, let's go through this question first, question number 1, before we move on, just to illustrate what we've learned so far. So consider gallium arsenide at 300 Kelvin with doping concentration of Na0 and Nd1016. So is the gallium arsenide p-type or n-type? Okay, on. Is it p-type or n-type? Na equals 0 and Nd equals 1016. Okay, straightforward, right? 1016. Nd 1016, therefore is n-type. Okay, so assume complete ionization. So this is the key. Assume complete ionization. So that means your electron concentration will be equal to the value of Nd, right? Because of complete ionization. So N equals to Nd, just like what we discussed during we talk about law of mass action. Okay. Assume electron and hole mobilities given in table 5.1 below, right? Calculate drift current density. If the applied electric field is equal to 10 volt per cm. Okay, so we're talking now about gallium arsenide, and at 300 Kelvin, if you see in this table, and low doping concentration, the mu n will be equal to 8,500 centimeters squared per volt second, and for hole is going to be equal to 400 centimeters squared per volt second. However, this is an n-type gallium arsenide, so you're going to need to use the n-type, right? So since ND is much bigger than ND, oh sorry, ND is much bigger than NA, or because NA is 0, by the way, the sample is n-type and the majority carriers are electrons. So in this case, due to 100% ionization, N is equal to ND. So minority carrier concentration, in this case, you can still calculate though, the minority carrier concentration. So if you put this into the equation, use law of mass action, N times P equals to Ni squared. Therefore, you know the N. So if you want to calculate the P will be equal to Ni squared. So for gallium arsenide, the Ni is equal to 1.8. So previously we've discussed a lot on silicon, and silicon has 1.0 times 10 to the 10, right? 1.0 times 10 to the 10. But for gallium arsenide, you need to use 1.8 times 10 to the 6 for its Ni. So you square that over your N value, right? The value of N in this case is 10 to the 16. So therefore, your minority carrier concentration is 3 times 3.24 times 10 to the minus 4 per centimeter cube. And this is very low, right? Very low, 10 to the minus 4. So before this, when we talk about silicon, we talk about a few examples, and the examples were like 10, 16 as the majority, and therefore 10 to the 4 as the minority, right? Or 10, 17 and 10 to the 3, which is still high if you compare to this. So this in this case, the minority is like 10 to the minus 4, very, very small, 0.00 something, okay? So this is very small. So that's why you can approximate the NA as nothing, okay? It's too small. So for this extrinsic N-type, the drift current density is given by, so if you're given this sort of question, first thing is write the equation first. Write the full equation before you simplify to the majority carrier that you need to calculate. So J drift equals to E times mu N times N plus mu P times electric field, and can be approximated as E times mu N times ND times E, because we have removed this component, right? We've removed this component because it's 0 to start with, and then if you did the calculations now, it's very, very low, so it can be omitted, right? Can therefore be omitted. So you can approximate your J drift to be equal to this: electron charge times mobility of electrons times electron concentration times electric field. Just plug in all the values. Electron charge times 8,500 from the mu N of gallium arsenide, and then your ND is already given, right? 10 to the 16 times your electric field, 10 volt per centimeter, as given by the equation. So that will give you 136 ampere per cm squared, contributed by electrons only. Okay, electrons only. There's no hole component because minority carrier concentration is too low. However, if you're given, say, if you go back to the minority carrier concentration here, the law of mass action, if your doping level is too low, okay, if your doping level is too low, your N will be very low, so your denominator will be very low. So your P will therefore be a bit higher than this, right? Because your Ni squared over lower value will give you a higher value of P. So at that point, you need to calculate, you need to try to calculate the J drift, which is contributed by the hole, and see whether the value of the current density is significant enough to contribute to the total current density. Okay, so in this case, if you see the negative here, so you can roughly say that the current density contributed by the drift of hole should be very low. and therefore it can be emitted. Okay. However, if your N value is a lot lower than this, so your P value will be higher than this, and therefore it might contribute to the total current density asked by the question, right? So try to check out first. So comment on this, significant drift current density can be obtained in a semiconductor applying relatively small electric field. So even though our electric field in this case is only 10 volt per cm, okay, so the resulting current density due to electron is high. So 130 amp, 136 amp per cm squared is high. Okay. Note from this example that the drift current will usually be due to primarily the majority carrier in intrinsic semiconductor. So, well, most of the time, we'll see that the total current density will be contributed mainly by the majority carriers. Okay. Unless the question is testing you by giving the majority to be a lot lower than this, maybe a couple of orders of magnitude lower instead of 1016. Okay, at that point you may see a more significant contribution of your minority carriers towards J drift. Okay, total current density. So is it okay? This example, is it clear? Can you follow this? Yep, quite straightforward, yeah? All right, so let's move on. Conductivity, we have covered conductivity last time, but very briefly. So the reciprocal of conductivity is resistivity. So I've discussed this one before a couple of times. The reciprocal of conductivity is resistivity. So we've discussed this last time when we talk about the curve of resistivity against carrier concentration. As shown here, we've also discussed this one before. I ask you whether you know the doping level if you're given a wafer, a silicon wafer, for example, with resistivity of such and such, right? So you can always come back to this curve and check it out. So resistivity is given by the inverse of conductivity, and therefore, since we've discussed conductivity, so it's the inverse of 1 over electron charge times mu nn plus mu pp. Okay, so mu nn and mu pp. So you can get these two values from the curve of your mobility curve and electron concentration or hole concentration curve. So let's recap this. The first one is resistivity against impurity concentration for silicon at 300 Kelvin for both p-type and n-type. Okay. So for example, if you're given a wafer with 1 ohm cm, so normally it's not labeled on the pack. Say if you're given with 1 ohm cm, so you'll need to come to this line and then check if your wafer is n-type or p-type. So if your wafer is p-type, you need to check it out here. So that's about 1 to 2. So that's about 2, let's say 2E16, right? 2E16 per centimeter cube of holes in your silicon wafer, right? On the other hand, if it's n-type, then you need to come to this point and it's slightly lower than 1016. So that's perhaps somewhere around 8E15 or so. Okay, so that's close to 1016, but slightly lower than 1016. Okay, so you need to check it out whether it's p-type or n-type and verify the resistivity. So you can also get this from gallium phosphide curves, gallium arsenide, germanium, right, at the same temperature for both p-type and n-type. So sometimes the question doesn't give you any figures like this. So maybe some doesn't give you this figure, but instead it'll just leave you with the dopant concentration of the majority carriers and then this graph. So you may need to come to this. You need to come to this graph to get the value of mobility or some other stuff, right? So resistance. I think you've learned this one in electronics, right? Have you? Belajar kan dalam electronics, resistance. Ada. Yep. So you've learned this one. So let's recap. Resistivity and conductivity are related. We've discussed before. Conductivity is equal to 1 over resistivity, also equal to J over E. And resistance of a slab. So this is the whole slab. Okay. This is the whole slab. So the resistance of the slab is given by rho L over A. R equals to rho L over A, where rho is the resistivity, L is the length, A is the area. Okay, quite straightforward, right? This times this, height times width. And L is given, and then you can know your value of R, resistance. So if we have this, and then we want to do the JE, the current density across the slab. So this slab is only an example. Later on, when we discuss about devices, for example, if you talk about MOSFET, metal oxide semiconductor field effect transistor. So you're going to see that we're going to go through this later on, but this is only you're going to have a gate, you're going to have an oxide under the gate, and you're going to have a channel, you're going to have a source drain on the left and on the right, and you're going to have a channel in between. Nanti you akan guna this concept of slab in order to see the current through the channel. Okay, current through the channel. Cumanya slab ni is a big thing for you to start with, and then we need to scale it down to our semiconductor devices. Okay, question. Another one. Concentration of donor impurity atoms in silicon is Nd equals to 1015. Okay, N-type or P-type? Donor impurity concentration, N-type. Okay, jangan silap dah hal ni ya. So it's very straightforward. Donor N-type, acceptor P-type. So in silicon, assume electron mobility of mu n equals to 1300 and hole mobility of 150. Okay, hole mobility of 450 and mu n of 1300. Calculate the resistivity of the material and what is the conductivity of the material. Okay, so that's resistivity of the material. So how to do that? Very simple. Resistivity is equal to 1 over conductivity, and the majority carrier in this case is N-type, electrons 10 to the 15. So you can just omit the whole component, therefore. So Q times or E times mu N times Nd. Okay, so very straightforward. Electron charge times 1300 times 10 to the 15. So you're gonna get 4.81 ohm cm. Okay, 4.81 ohm cm. So therefore, leading to the second question, what is the conductivity of the material, which is the inverse of resistivity? 1 over 4.81 equals to 0.21 ohm cm inverted, right? Ohm cm minus 1. Right, another one. A silicon sample is 2.5 cm long, okay? 2.5 cm long and has a cross-sectional area of 0.1 centimeter squared, right? So on the slab, right? Question on the slab. The moment you see this length and area thing, is going to be on the slab. So the silicon is N-type, so it's declared already N-type. Donor impurity concentration of 2 times 10 to the 15. Resistance of the samples measured and found to be 70 ohm, right? So R is already given. What is the electron mobility? So it's just rearranging the equation to get the intended parameter. In this case, it's electron mobility or mu n or mu e, right? N or mu e. So the very same thing. So R is given, R equals to rho L over A, okay, or also equals to L over conductivity times area, and you can convert the conductivity into Q mu N, okay, Q mu N, so then rearrange the mu to be the header, and then you're going to be end up with L over E N D R A, and just plug in the length is given, 2.5, then E is known, E is fixed, right? So ND is known, 2 times 10 to the 15. R is known, 70 ohm. A is known, 0.1 centimeters, 0.1 cm squared. So therefore, the mu n is 1116 centimeters squared per volt second. Okay. So is it okay so far? This equation, this example, straightforward, right? Just rearranging the equation. Okay. That's all. So far, okay. Right. Good. So let's cover a little bit on diffusion. So we have covered drift. So let's go through diffusion now. Diffusion is the process whereby particles flow from a region of high concentration towards low concentration region. So just like what we discussed now, is moving from high concentration region to lower concentration, just like when you make your tea. Okay. If the gas molecules were electrically charged, the net flow of charge would result in diffusion current. So since we're talking about charges, electrons and holes, so it's gonna be current associated with the movement, just like current that we get from drift of holes and electrons. Okay, the moment you have the charges, it's gonna contribute to current related to its carrier transport mode. So in the first case, it was drift. So in this case, it's gonna be diffusion. Okay. So watch animation here. Let's go to the diffusion animation. Sorry, loading now. Right, can you see the web? I'm not sure if I need to reshare, but I think you can see right away. Ah, okay. So if I click here, then you can see right away. I don't have to reshare. Okay, this is about diffusion then. Okay, diffusion, well, this is more about solar cells, so that's why the explanation always starts with something on solar cell. Oh, I cannot. All right, so that's the thing. I cannot move my cursor here. Kejap, tadi gerak pula. So I have to stop sharing and go to the website then. Okay, diffusion. Let me. Okay. So can you see the slide? No, not the slide. The website now. Yeah, nampak kan? Okay, good. Okay, so diffusion, you can come here and see the animation for yourself. So it's all about moving from high concentration gradient to low concentration gradient. So in this case, diffusion is random scattering of carriers to produce uniform distribution. So in this case, in this animation, a quarter of the carriers move to the right and another quarter move to the left, and remainder stay put, move up and down. So net movement, left and right. So this is random diffusion, okay? So net movement to the left and to the right, so it's moving almost equally in terms of its content. Okay. So how about this? So this one particle. Okay. So it starts with macam contoh lah, just like making tea. So you uncang tu will be the tea bag will be the red part or the blue part, and then eventually it's going to be distributed. Okay, restart. So you start off like that. So it's going to fill the space in order to fill the low concentration region and eventually reach equilibrium condition. Okay, now this is all equation. Okay, let's go back to the slides. Let's go for another few minutes. It's 10:48 already. Okay, now I'm on the slides. So diffusion is the movement of electrical charges due to concentration gradient. You've seen just now. So when you have charges moving due to diffusion to establish equilibrium due to the concentration gradient, the presence of concentration gradient, there'll be current density associated with the flux of the carrier movement as well. Okay, so in this case, we're going to have current density due to the hole and current density due to the electron diffusion. Okay, for in this case, the current will be given by for hole is going to be equal to Jx equals to negative, all right, negative sign, Qd dp dx. Okay, Qd dp dx. So Q is the electron charge, D is the diffusivity or diffusion constant, and dp dx is the gradient, right? Gradient seen by the holes from the original region compared to the new region, to the neighboring region, high concentration to low concentration. Similarly, for electron, the current density related to the electron diffusion will be equal to Jx times positive in this case, so it's inverse, positive Q d dn dx. So the very same equation, but you need to put the negative sign for electron. Okay, so for hole, for hole, dn dx is the very same thing. Concentration gradient from the high concentration region to the low concentration region, dn dx. So d is the flux related to the flux of the gradient. We call it diffusion constant. It's normally given. Okay, has a unit of cm squared per second. Diffusion occurs whenever you have a gradient. So from when you see two concentration regions, or high concentration and low concentration, you're going to see movement of carriers, electrons and holes. So in this case, for example, you can see two graphs. So the first one is electron concentration curve on the y-axis against distance on the x. And then the second graph is about hole concentration against distance on the x as well. So if you're talking about the concentration gradient, so we can see that electron flux, if electron flux is moving to the left, so the current electron diffusion current density will be moving to the right. So it's going to be opposite, just like what we saw in the drift current. Okay. On the other hand, if you look at this, the hole is moving to the left. If hole is moving to the left, then the whole current density will be moving to the left as well, just like what we got on our drift current. Okay. Okay, this is another example. So let me finish it off here. So another example. So for example, if you're talking about different duration, if you characterize the movement of the profile of the movement of electrons by time, so this is going to be your T number 1. When you first started, so the profile when you just started, and then over time it's going to be diluted, it's going to be moving to the right, so your peak is going to reduce a little bit, and then it's going to be more distributed. Okay, it's going to move to the right, so therefore the original concentration will be depleted a little bit, reduce here and expand to the right. And then if you leave it longer to T3 is going to be reduced as well. Further, the peak is going to be reduced, and it's going to be more distributed. So if you want to plot T4, for example, it's going to be like that. It's going to be more distributed. Okay. So DE and DH are different, as was the case with mobility. Diffusion coefficient and mobility are related by thermal voltage. We've discussed this one before, KT over Q. Okay, thermal voltage for the thermal excitation. So you can relate, okay, thermal voltage is equal to 26 millivolt at 300 Kelvin. And D and mu is related to the thermal voltage by this equation. We call it Einstein relation. Okay, Einstein relation. D over mu will be equal to KT over Q. So it's for electron, dE over mu E, KT over Q as well. And then also applicable to the whole dH over mu H, also equal to KT over Q. So, and this is called Einstein relation. So I think I'm just going to stop here for a while. So we're going to do a bit of calculation tomorrow on diffusion. Then we're going to finish off with Hall effect. All right, so that's all for today. So far, so good. All right, good. All right, then I'll see you tomorrow 1 to 2. Okay, I'll see you tomorrow 1 to 2 p.m. Bye-bye. Take care. Assalamualaikum. Stay safe.